What if the most famous black hole in our galaxy isn't a black hole at all? For decades, astronomers have pointed to a violent, invisible monster at the center of the Milky Way, a 4.6 million solar mass object known as Sagittarius A star. We watched stars whip around it at nearly 10% the speed of light. We celebrated when the first image of its shadow was revealed to the world. Case closed, right? But now, a group of researchers is challenging that entire narrative. They're not saying the object at our galaxy's heart is smaller, or weaker, or less extreme. They're saying it might be something even stranger. A dense, compact core of dark matter that mimics a black hole so perfectly, we may have mistaken one for the other. And if they're right, this doesn't just change what's at the center of the Milky Way. It could rewrite what we think dark matter is, and what black holes really are. For years, the case seemed airtight. At the very center of the Milky Way sits an object so massive and so compact that nothing else seemed capable of explaining it. Stars known as the S stars whip around this invisible point at mind-bending speeds, some reaching nearly 10% the speed of light. One of them completes a full orbit in just 16 years, tracing a tight elliptical path around something we can't directly see but can absolutely feel through its gravity. Measurements show that whatever is sitting there packs the mass of roughly 4.6 million suns into a region smaller than our solar system. There are no visible stars there, no glowing cluster bright enough to account for that mass, just an intense gravitational grip holding everything in place. For decades, observations from powerful instruments like the Very Large Telescope tracked these stellar motions with incredible precision, and every new dataset pointed to the same conclusion. Only a supermassive black hole could compress that much mass into such a tiny space without flying apart. Then, in 2022, the world saw what many called the final piece of proof, the glowing ring captured by the Event Horizon Telescope. It looked exactly like what Einstein's equations predicted, a bright halo of superheated gas wrapped around a dark center. To scientists and the public alike, it felt definitive. The monster at the center had finally been seen. But here's the part that changes everything. What if that conclusion, as convincing as it seems, was built on an assumption? What if the evidence proves something massive and compact is there, but not necessarily a black hole? And that's where the alternative begins to sound almost unbelievable. Instead of a black hole, some researchers now propose that the object at the center of the Milky Way could be an ultra-dense core made of dark matter. Not the invisible halo we usually imagine surrounding galaxies, but a tightly packed clump of exotic particles compressed into an incredibly small region. This isn't just swapping one mysterious object for another. The idea goes much deeper. According to the team behind the theory, the supermassive object in the center and the vast dark matter halo stretching around our galaxy may actually be the same continuous substance, one unified structure with a dense core at the center and a diffuse outer envelope extending far beyond the visible stars. The key lies in a specific type of dark matter, ultralight particles belonging to the fermion family. In this model, these particles don't just drift loosely through space. Under gravity, they can organize into a super compact core dense enough to mimic the gravitational pull of a 4.6 million solar mass black hole. Around that core would sit a broader halo, gradually thinning out into the outer galaxy, but still physically connected as part of one massive system. And here's the striking part. When scientists ran the numbers, this fermionic dark matter core was able to reproduce the exact stellar motions we attribute to Sagittarius A star. The S stars would orbit the same way. The mysterious G sources would behave the same way. From a gravitational standpoint, nothing would look different. But if this structure can truly imitate a black hole so perfectly, then the real question becomes unavoidable. What convinced us it was a black hole in the first place? And could that evidence have another explanation? The turning point didn't come from the center of the galaxy. It came from its outer edges. In 2022, the European Space Agency's Gaia mission released one of the most detailed maps of the Milky Way ever created. By tracking the precise motions of billions of stars, Gaia allowed astronomers to study how our galaxy rotates on the largest scales. And what they found was subtle, but unsettling. The outer regions of the Milky Way appeared to show a slight Keplerian decline, a slowdown in rotational speed farther from the center, more in line with how gravity behaves around a single, concentrated mass. That's a problem for the standard model of cosmology. In the widely accepted lambda cold dark matter framework, dark matter forms a broad, extended halo that should keep rotation speeds relatively flat, even far from the galactic core. Instead, Gaia's data hinted at something more compact, a halo structure that tightens and fades in a way the traditional cold dark matter model struggles to explain. And this is where the Fermionic dark matter proposal starts to look less like speculation and more like a contender. Unlike standard cold dark matter, ultralight fermions can form a dense central core with a more sharply defined outer halo. That configuration naturally predicts a rotation curve that declines in the way Gaia observed. In other words, the same model that replaces the black hole at the center also appears to fix a subtle but growing tension in our understanding of the galaxy's outer motion. If true, that means this isn't just about what's happening at the core. It could mean we've misunderstood the entire structure of the Milky Way from the inside out. And that realization forces us to revisit the one piece of evidence everyone thought sealed the deal. Because in May 2022, the world saw something historic. After years of global collaboration, the Event Horizon Telescope revealed the first image of the object at the center of our galaxy, a glowing, uneven golden ring surrounding a dark center. Headlines declared it proof. This was Sagittarius A star, the supermassive black hole itself. Einstein was right. The case was closed. But here's the detail most people missed. We didn't actually see a black hole. By definition, a black hole cannot be directly observed. Its event horizon traps light completely. What the telescope captured was superheated plasma whipping around the central object at near light speeds. The bright ring is radiation from that infalling matter. The darkness in the middle isn't the object itself, but a shadow created as extreme gravity bends and captures light around it. That shadow became the ultimate confirmation in the public eye. It matched theoretical predictions almost perfectly. But scientifically, it proves something very specific. That there is an extremely compact, massive object bending light in a way consistent with strong gravity. It does not on its own prove the presence of an event horizon. And that distinction is small, but critical. Because if something else could bend light just as intensely, if something else could create the same shadow pattern, then the image doesn't end the debate. It reopens it. And that's exactly what happened next. In 2024, researchers pushed the idea even further, and this is where things took a dramatic turn. Using detailed simulations, they showed that a dense core made of fermionic dark matter could cast a shadow strikingly similar to the one captured by the Event Horizon Telescope. Not identical in every microscopic detail, but close enough that, with current resolution limits, the two scenarios could be nearly indistinguishable. The reason is surprisingly simple. Dark matter doesn't interact with light, which makes it effectively invisible. But gravity doesn't care whether something is a black hole or a compact dark matter core. If the mass is squeezed tightly enough, it will bend space-time in extreme ways. Light passing near that dense core would still curve dramatically, still swirl into tight orbits, and still produce a central darkness surrounded by a glowing ring of hot gas. From our vantage point 26,000 light-years away, the result could look almost exactly the same. That realization shifts the conversation entirely. If a dark matter core can reproduce the orbits of the S-stars, match the galaxy's rotation curve, and mimic the famous shadow image, then the evidence for a traditional black hole becomes less exclusive than we thought. It doesn't disappear, but it no longer stands alone. And once two competing explanations can both account for the same observations, science doesn't settle the debate. It sharpens it. Because now the question isn't what fits the data, it's what fits it better. That brings us to the ultimate test. One that could finally separate black holes from dark matter cores. Scientists are looking to the so-called photon rings, narrow, circular bands of light formed when photons orbit a true black hole multiple times before escaping. These rings are a unique signature of an event horizon, a feature no dark matter core, no matter how dense, can produce. Future observations with instruments like the Very Large Telescope, VLT, aim to detect these rings around Sagittarius A star. If photon rings appear as predicted, it would strongly confirm the black hole scenario. But if they fail to materialize, the dark matter core model gains serious credibility. This simple observation could settle a debate that has challenged astronomers for decades, turning speculation into evidence, one way or the other. It's a high-stakes test, not just for our understanding of the Milky Way, but for physics itself. If the dense dark matter model is correct, it could reveal that the universe holds objects far stranger than black holes, with galaxies shaped by a single, continuous substance stretching from their centers to their outer halos. And if it isn't, then we get to celebrate Einstein once again, confirming that the universe really does hide monsters at its core. Either way, the coming years promise to reshape what we know about the heart of our galaxy. And the implications don't stop at our own galaxy. If a dense dark matter core can mimic a supermassive black hole, it forces us to rethink how we interpret the centers of countless other galaxies across the universe. What we've long assumed to be monstrous black holes could, in some cases, be entirely different structures, massive, invisible concentrations of exotic particles shaping the motion of stars and gas without ever forming an event horizon. It also raises questions about the very nature of dark matter. For decades, scientists have struggled to detect it directly, even though it makes up most of the matter in the universe. If fermionic dark matter can organize itself into dense, compact cores, then it's not just a diffuse halo floating through space. It's a dynamic, structured, and perhaps even observable component of galaxies. That would revolutionize our understanding of cosmic architecture, linking the smallest subatomic properties of dark matter particles to the largest structures in the universe. And yet, for all the excitement, the truth remains out of reach. The photon ring test is still pending, and until it's conducted, both models remain viable. The universe may be preparing to reveal a secret even stranger than we imagined, or confirm what we've believed all along. Either outcome will challenge our assumptions and push the boundaries of what we think is possible in the cosmos. In the end, the debate over what truly lurks at the center of the Milky Way is far from settled, and that's what makes it so exciting. For decades, we've accepted Sagittarius A star as a supermassive black hole, the ultimate cosmic heavyweight controlling the dance of stars around it. Yet now, the possibility that this object is instead a dense dark matter core forces us to reconsider everything: the nature of black holes, the behavior of galaxies, and even the properties of the mysterious substance that makes up most of a universe. Whether future observations confirm the black hole, reveal photon rings, or support the dark matter hypothesis, one thing is certain: the heart of our galaxy is more fascinating and mysterious than anyone imagined. It reminds us that science is never truly settled. Every new discovery opens the door to questions we didn't even know to ask. And as we peer into the darkness at the center of the Milky Way, we're not just observing stars and shadows. We're confronting the boundaries of our understanding and glimpsing the hidden architecture of the universe itself. The universe may not give up its secrets easily, but one thing is clear: the story of Sagittarius A star is far from over, and what comes next could rewrite the way we see the cosmos forever.